So in our last video, we learned about the normal distribution, we learned about the empirical rule, and we did say that our empirical rule says if we want to find the middle 95% of the scores, it's always going to be our mean plus or minus, sorry, I'm having a hard time today, the mean, mu, plus or minus 2 times the standard deviation. But what if we wanted to find, say, like the middle 90% of the scores or the top 10% of the scores? We haven't learned how to do this. And what if we wanted to do it for like a normal distribution that has a mean of 570 and a standard deviation of 51? Okay. And so it turns out that there are so many possible normal curves, we couldn't make a table of probabilities or formulas for all of them. Instead, what we'll do is we'll just have one table of probability for the standard normal curve. And so what we'll do is for any situation, we can always standardize any observation or any random variable by taking z, which is going to be our x value, minus the mean of our distribution over the standard deviation of our distribution. So what this means for us right now is if we have a random variable x that's normally distributed with a mean mu, standard deviation sigma, we can standardize it with this formula, z equals x minus mu over sigma. And our new random variable z has a standard normal distribution with a mean 0 and standard deviation 1. Okay, so that's what you need to memorize. Z has a mean 0, standard deviation 1. So z is normally distributed, mean 0, standard deviation is 1, so variance is 1 squared. So for this example, let's see, how would we standardize the normal with a mean of 64.5 and a variance of 6.25 from our example 1.24 or 124? Okay, so this means that it's normal. Mu equals 64.5. Our variance equals 6.25 because our textbook always gives the variance there. And that means that sigma is the square root of that, or just 2.5. So what will you do every time you want to standardize is you do z equals x minus the mean over the standard deviation. Or in our case, it'd be x minus 64.5. It's going to be x minus 64.5 over 2.5. So that's what we'll do for every observation. We can standardize it using this formula. So you'll notice a few things here. So I drew a picture. This first one has the numbers like 62, 64.5, 67. That kind of sounds like our original values. And so this graph here would be my original data, which we represent with an x. So x is kind of always your original. And then down here we have the z's. And notice my z's has a 0, 1, 2, 3, etc. So this is our standard normal curve, or our standardized values, and we always represent that with a z. So x will always be your original data, z will be your standard normal. And what I kind of want you to see here is that you can line these up. So this 64.5, that was our average, but when you standardize it, what's the new average? The new average would be 0, okay, which you could see by if you plug in 64.5 minus 64.5 over 2.5, we get 0. Okay. So let's go ahead and try our next example. Let's standardize our following observations. So these are just a bunch of different examples. One of the first things we might want to do is we might just want to remind ourselves that we use the notation normal has a mean and variance. Okay, so number one, x equals 3, and we have a normal distribution of 2 and 9. So this means that our mean is 2, our variance is 9. So if you actually want to find your standard deviation, you do the square root of variance, which is 3. So kind of unfortunate that this is a 3 and that's a 3. But that's okay, we can still do it. So z is always equal to x minus mu over sigma. So we have a 3 for x minus 2 for our mean divided by 3 for our standard deviation. So I just don't like having the same number in there twice. But we get 1/3, and so you've standardized it. Okay, not too bad. So in part 2, a person gets a score of 273 on a test with a mean of 290 and a standard deviation of 16. Let's assume our test scores are normally distributed. So here we have x equals 273. Our mean is 290. And our standard deviation, notice it just told us standard deviation, not variance, so I don't have to take the square root. And it says assume that the test scores are normally distributed, so we know it's normal. So z is always again equal to x minus mu over sigma. So we'll get our 273 for x, our mean is 290, our standard deviation is 16, so this gives me negative 1.0625. So there's z. Notice how z is negative. That tells you that your x value was less than the average, and 270 is less than the average of 290. Okay, what I want you to do now is pause your video, take a couple minutes, and try the next two on your own, and then turn the video back on to see if you get the same answer. So for number 3, the length of baby Smurfs has an average of 10 inches, so mu equals 10. Our standard deviation is 1.7. Again, they gave a standard deviation, so we don't actually have to take the square root. Let's see, the baby Smurf bill is measured at 9.3. So your actual data or value is always going to be your x. And let's assume the lengths are normally distributed. If it's not normal, there's no point in standardizing. So z equals x minus mu over sigma. So our x was 9.3, our mean was 10, our standard deviation is 1.7, so we get negative 0.41. And number 4, x equals negative 31. Our mean is negative 40, and our variance equals 3. So if our variance is 3, that means our standard deviation is the square root of 3. So z, sometimes you might get tired writing down these formulas, but I write them down every single time I do a problem. So x is negative 31, the mean is negative 40, and our standard deviation is the square root of 3. So this gives me 5.20. Okay, this is positive, so this tells me that my value was higher than my average. So negative 31 is higher than negative 40. So that's how you standardize. Once you standardize, here's a few things about the standard normal distribution. It has a mean of mu equals 0 and a variance of 1, which we write this way. We have our PDF that has this notation. This is a Greek phi for phi. And I guess that's why I couldn't remember which one it was, because people do either one. So you can call it phi or phi. This is the lowercase is there at phi, and uppercase is like that. Okay, so we do the lowercase for our PDF and uppercase for our CDF, just like we did with our little f and capital F. Okay, and so here's what the PDF is, but the CDF, you would have to integrate this PDF, and it turns out you can't actually integrate that and get a closed form. And so instead we'll have to use a table or a calculator to find all of our probabilities. Now on your homework and things, if you know how to use your calculator to find probabilities, great, do that. Okay. If you don't, then you can use the table. Okay. And unfortunately, a lot of people don't have calculators to do and stuff. I still have to teach you how to use the table. So here's just a few pictures again from your textbook. Okay, so this is what our normal curve looks like. Standard normal curve. It has a mean of 0, a variance of 1. That also means a standard deviation of 1. Okay. You can see the CDF or PDF up here. Over here, you'll see that they drew in the curve again. The CDF, or the cumulative probabilities, would be all of the area under the curve. So that's why they have that CDF of the capital phi. Okay, they graphed out the CDF. That's not really that interesting to us. This is, though. So in this one, this phi of x equals the probability that x is less than or equal to a specific number, right? And so the CDF always gives you area to the left, which is why on these tables, like right here, you see that we want to find this area to the right of x. Well, our CDF gives us areas to the left. So to find the area to the right, you have to do 1 minus, or use the complement rule. part over here might not look as interesting to you yet, but this is just our negative x value because we put a positive x here, which means that we'd have a negative x here. This is just kind of our symmetry. It turns out that if you have a positive x value here and negative x value here, the area to the right of positive x and area to the left of negative x will always be the same. Those areas are the same. And if you want the area to the left, you just plug it into your CDF. Okay, this is what it looks like in your textbook. So you'll have your x value, and I'll tell you the area to the left. So our table gives area to the left. And then there's also something here with your critical values, which we'll worry about in a minute when we get to that. Okay, now in your textbook, in your guided notes, at the very, very back, there's a standard normal curve table. And that's the one that we'll actually use in this class. You can't use the one in your textbook. You get the exact same answers. But as far as the test, I went ahead on the test. I give you the one that I made up, which basically I just had to redo it so I could give it to you in your guided notes. And I'll put on Canvas too so you can print it off. I suggest just having a couple copies and putting one right next to you as you do your homework. I actually like having lots of copies because I write on mine all the time. So what we'll do is we're going to practice. We're going to find our table to find these different probabilities. And one of the things I recommend doing is always drawing pictures. Don't memorize things like it has in the book. Just draw pictures, okay? So if we want the probability that z is less than 2, so here's 2. I want everything to the left of it, so I'm drawing it like this. Now notice this is probability that z is less than 2. Okay, that's our CDF at 2. Or basically, we just look at the table. You'll find that the book does all of these notations. I don't actually usually write out the notations because I can just kind of do it in my mind with the help of the pictures. For this problem, I know that I just need to look up the number 2 on my table. So I go to my normal table, my standard normal table, and you'll see that it's set up like this. So you have values to the left, on the left side here, and you have values across the top. So these are our ones and tenths place, and these are our hundredths. And this is our ones and tenths. It was just the easiest way for them to organize the table, to put lots and lots of numbers on here. So what you'd have to do is you try and find the number z equals 2. You'll notice on the first page of the table, these are all negative z values, so I actually need the second page of the table. And I'll go down to z equals 2.0, and then go across the O, so 2.00. Find the intersection, and it's 0.9772. So this is 0.9772. So that's my area here, 0.9772. So let's kind of go down the left side here. I haven't organized them left side and right side. My next one says find the probability z is greater than or equal to 2. So here's my 2. I want the area to the right. My table, though, only gives me areas to the left. And in fact, I already looked up that too, and it said the area to the left was 0.9772. So how would you find the area to the right? You do 1 minus 0.9772, or 0.0228. So this would be, we have to use the complement rule, so you do 1 minus the probability if you look up 2, or 0.0228. So this was our complement rule. And our next one says find the probability that z is less than or equal to negative 2. So here's my negative 2. We go to the left. Well, that's just going to be my CDF at negative 2. So I can go to my table. I look up my negative 2.00 is going to be 0.0228. So we get 0.0228. But wait, that seems very similar, right? That's what I got up here for the area to the right of positive 2. So this is what I'm talking about when I say symmetry, is the area to the right of positive 2 is equal to the area to the left of negative 2. It's very symmetrical. So instead of looking it up again, I could have just gone with what I had there. So I could have used symmetry. And you'll find on all of these, there's always lots of different things that you can do to get the same answer. You just have to practice. So this next one, find the probability that z is less than or equal to 3.18. So 3.18 would be about here. I'm going to do everything to the left, so that should be a pretty big number, pretty close to 1. But that would just be my CDF at 3.18. So I go to my table, I'm looking for a positive, so that's on the second page. This is what I mean by printing out so you can draw on it. So 3.1 is this row, and I need 3.18, so that would be this column. So where do they intersect? Right here at 0.9993. So 0.9913. Again, this is in the very back of your guided notes, and I put it on Canvas so you can just download it. Let's see, my next one is z is less than or equal to 4.5. So 4.5 would be about here. So I'm going to start here and go all the way to the left. Notice, just looking at my picture, it kind of seems like that's going to be everything, right? I think it's probably going to be about 1. Let's go to our table and see. So notice my table only goes to 3.49, and at this point it's really, really close to 1. So 4.5 is probably somewhere over here, and that's going to be even closer to 1. And so in situations like this, you say, okay, if I was going to look this up, and again, artificial limitations, you say, okay, that's the CDF at 4.5, but it's basically 1. Because it was off the charts, and I can tell by looking at the picture that it should be almost everything here, so it should be basically 1. And one more thing here. So the probability that z is now between 0 and 2. So here's my 0, here's my 2, and I want everything in between them. Now this is interesting because we don't actually have a table that gives us values in between. It only gives us everything to the left. And in fact, if I was going to look up that 2, if I look up 2 on my table, it gives me 0.9772 because that's the area from 2 all the way over. And if I was, and that's obviously too big, I don't want to go from 2 all the way over. I want to stop at 0. So how do you stop at 0? Well, what you do is you could look up the 0, you could look up this area and subtract it out. So let's go look up 0. So here's 0.00, 0.5. That makes sense, right? It's centered at 0, so we should have half the probability on either side. So if I look up the 2, it gives me everything to the left, but that's too much. So if I look up from the 0, that's the area to the left that I didn't actually want, and I can subtract them, and that will give me just what I do want in the middle. So anytime you want the area in between two numbers, we'll always do the subtraction. So you'll look up the bigger number, and then look up the smaller number and subtract them. So you always do the bigger one first. So 0.9772 minus 0.5 gives me 0.4772. Now, if you happen to subtract them in the wrong order, what will happen? You'll just get a negative value. And if you get negative value, you know you did something wrong because you can't have negative probabilities. And we'll stop our video there. And the next time we have class, we'll go ahead and try the next page, which is just some more practice and keep learning about the normal curve.